Welcome to the Flight Readiness Review of Atlas UAV team from Istanbul University Cerrahpasa. Quadcopter design was preferred considering weight, flight time, power efficiency and cost criteria. A stable UAV had been designed to be able to capture high-quality images and have a decent maneuverability. UAV's airframe consists of a combination of two carbon fiber plates which are processed in high-precision CNC. The electronic layout is set on these two plates by taking into account the COG of the UAV. In addition, it was decided to use 4 separated landing gear attached to the rotor booms for stable landing and takeoff. Carbon fiber is used for both airframe and rotor booms due to its lightweight and high-strength material properties. (3D printing PLA parts are used for fittings that can be easily reproduced and replaced. There is a 6S 26,000 mAh lithium polymer battery in the aircraft to power all the electronic components. The propulsion system of the UAV consists of 4 BLDC motors, 22-inch carbon fiber propellers, and 60 ampere electronic speed controllers. Pixar Cube Black is used as the autopilot board. This board was chosen due to its fully compatible with Quadcopter autopilot software used by the team and has proven itself in flight tests. Here 3 GPS with RTK system is used to provide high precision location data. To meet SUAS mission requirements, NVIDIA Xavier NX is chosen as a companion computer. To get more precise image quality and prevent camera vibrations, Sony a6000 camera is configured with a custom-made gimbal system. A pair of RFD 900 Plus long-range telemetry, radio link RC receiver and transmitter, and Wi-Fi link with 2 Rocket M5s are used in communication system to provide seamless connection. Sony a6000 DSLR camera is triggered by Xavier NX. For autonomous ODCL mission, taken photos are processed on Xavier NX by using YOLO, OpenCV, Key-Means, and our custom technologies. Both handled and not handled photos were sent to REST API with a related JSON file. Open source GCS software mission planner is modified according to the tasks to be performed and the needs of the team. Atlas Manual ODCL Review is developed to classify ODCLs manually, and cropped images can be easily reviewed on ODCL and image review interface. Also, it is possible to change camera settings during flights by using Atlas Camera Control Interface. The team will attempt all the tasks except the airdrop in the competition. Most mission tasks are accepted to be performed with high confidence. SUAS point calculator was created according to the team's mission expectation, and the total mission point was calculated. By using the finite element analysis method via ANSYS, the strength of the carbon fiber booms and the motor mounts had been analyzed. The selected motor model was tested before being used on the UAV, and the thrust value provided by one of the motors was measured as 5.4 kilograms. Missions are simulated before being tested on the UAV, thus, possible accidents are prevented. Various components and systems on the UAV, such as electronic speed controller, motor, and power systems, are tested and calibrated before autonomous flights. After making sure that all systems are running properly, UAV is subjected to integration tests. For the precision of the flight, an auto-tune flight was performed, and the PID values of the UAV were optimized. To improve the flight capability, specific parameters have been changed. In addition to flight optimization, safety is also a very important subject for our team. There is a team member who will intervene immediately in case of potential dangers in the flight tests. The team conducted more than 35 autonomous flights, which corresponds to approximately 400 minutes of flight time. 16% of flight time involves manual takeover. The determined waypoints were first tested on the Atlas Planner GCS to determine UAV's attitude. On flight tests, more than 1,000 waypoints were attempted. The spline waypoint command is used to minimize the miss. The average miss rate at these tested points was calculated as 13 feet. The obstacle avoidance algorithm was developed using the A-star algorithm in the Python programming language. The obstacle avoidance algorithm is integrated into the Atlas Planner GCS so that the tasks can be recreated to pass outside the obstacles. Minimum distance to the obstacle and the number of waypoints to be created can be adjusted. The results in the table were reached first through the simulation, then in the tests carried out on real flights. The imagery system is composed of a 24-megapixel Sony Alpha A6000 camera with a custom-made 2-axis gimbal that is made to be small and lightweight. Also for stable image capturing and preventing of jello effect, PID control of gimbal mechanism is tuning advanced. In order not to be affected by environmental factors, Atlas Camera Control Interface has been developed. By using the interface, it is possible to change shutter speed, ISO, diaphragm, and other parameters on the camera during flights. A dataset of more than 6,000 photographs was created with aerial shots taken at different times. The dataset is increased by using photograph manipulation techniques. Custom detection model was trained on neural networks of YOLO, one of the most popular and fastest deep learning algorithms. Autonomous ODCL algorithm was optimized during the flight test and maximized its performance. As a result, the autonomous object detection and classification algorithm shows an excellent success rate as shown in the table. The localization algorithm was first tested in Unity real-time development platform. The main camera on Unity is created from scratch using Sony A6000 camera specifications. Accuracy was ensured by testing the algorithm created in the images taken from the UAV in virtual environments. After the latitude, longitude values were successfully obtained, real-life tests were started. On full mission tests, more than 75% of obstacles are located within 5 feet. After adding location data to the photos taken with the flight record, the mapping process will be started by using the Agisoft software. After the necessary quality adjustments are made in the Agisoft software, WGS84 Web Mercator is selected as the projection method. The mapping steps are as follows: adding photos, aligning photos, dense clouds, and building DEM and morphoMosaic. At the end of all these steps, our WGS84 Web Mercator map is ready. We decided to withdraw from the UGV mission within the consideration of negative effect on the flight time, the strategy of the mission, and the budget constraint. Full mission tests are demonstrated within 3 sections, which are SITL tests, ground tests, and flight tests. Simulations are made before each flight to test software and prevent mistakes. Developments on the flight parameters were firstly held on Gazebo and autopilot software in the loop simulations. After making sure that there was nothing inaccurate, the UAV was configured with these parameters. During pre-flight tests, all subsystems are tested and made sure that everything works stable for the mission demonstration. Assembling of subsystem is tested repeatedly and time is kept for getting better. Flight tests are done after pre-flight checks. During our flight tests, all subsystems are tested and made sure that everything works stable for the mission demonstration. Autonomous flights have been made including takeoff and landing. On average, 80% of waypoints can be captured with an accuracy of 13 feet. Our average autonomous flight score is 90%. Mission flights were completed with an average setup time of 7 minutes and a mission time of 22 minutes without timeout. Our autonomous object detection rate is 81% and geolocalization accuracy is 5 feet. Considering the data from all flights, the average score is obtained 70%. We aim to reach an 80% score by making improvements in ODCL and mapping areas until the competition. Thanks for watching us.